Let's do one more example. We have a machine that produces components needed for a software company. Probability of a fault occurring in the production of a single component has to be less than 0.02. A sample size of 50, that's n, is taken from the output and tested to see if any were faulty. A test was performed with these hypotheses that the probability equals 0.02 or the probability is greater than at a 5% significance level. So these being our hypotheses tells me that we're doing a binomial test where n is 50 and our probability of success is 0.02. So there's two outcomes. We either have a fault or we don't. And we're assuming that the faults are independent of each other, which is a requirement of a binomial distribution. So that kind of answers part A there. So what type of distribution? Now for the critical region, that is when our probability or p-value is less than our significance level of 0.05. So this is where we're going to make a table. So our hypotheses here, we're already told, are the p equals 0.02 or we're greater than 0.02. We're going to create a table in order to figure out what our critical region is. So I'm going to define in my calculator this binomial CDF where n is equal to 50, our probability of success 0.02. We're doing an upper tailed test greater than 0.02. So that means I don't know my lower bound. My lower bound is x. My upper bound is 50 because that's as high as we can go. So if I look at the calculator, I'm going to define my equation here. You can use any number that you would like. I'm going to define this as our binomial distribution, binomial CDF, 50 trials, 0.02. My lower bound is x. My upper bound is 50. Okay, now I'm going to add a list in spreadsheets. I'm going to switch this to a table and I'm going to select that function. So we're looking for the first value where our probability is less than our significance level. So less than 0.05, which is 4. So that means our critical region is everything bigger than 4 because all of these values have a probability that's less than 0.05. So our critical region is x is greater than or equal to 4. So the probability of making a type 1 error is the probability that we are in the critical region given our null hypothesis is true. So we already know the critical region, x is greater than or equal to 4. Our null hypothesis being true is that our probability is equal to 0.02. So we're going to do a binomial CDF again. N is still 50. Our null hypothesis is 0.02, so we're assuming that is true. Our lower bound is 4. And our upper bound is 50. And I should be getting this probability right here. Open up a calculator page and do this probability. So probability distributions, binomial CDF, 50, 0.02, 4, 50. I do get what was in my table, 0.0178. So the probability is about 1.78% of making a type 1 error. Now, we were told that the probability of actually making a fault is 0.04 rather than 0.02. So now we need to calculate a type 2 error, which is the probability that we're in the acceptance region, which is the opposite of our critical regions, given that our probability is actually 0.04, what they told us it was going to be. And so since our critical region was greater than or equal to 4, our acceptance region is the opposite of that, which is less than or equal to 3, given the probability of 0.04. So we're going to do another binomial CDF. N is 50. P is now 0.04. So this P value matches this one. And then we're going to say from 0 to 3 for our lower and upper bounds. Gets us a probability of about 86.1%, which is a much higher probability than making that type 1 error.